Okay, so let me share the screen. Okay, so I know it's afternoon, so I will try to be quick. And as I told you, yeah, for tomorrow, we need to have everyone with a Gmail account. And also, even if you have the Gmail account, please activate your Google Earth engine, because it's a separate things you have to do. So, land cover mapping. These, of course, they are still the same course objective. In this case, for this presentation, I took some of the slides from another colleague, but essentially we are going to provide a summary of the principle, approach, and the classifier, the land use land cover. This is the acronym classifier. So first things, we have essentially spectral classes. So once we download the image and we convert to top of atmosphere, for example, we have our pixel with value, which is the reflectance. And of course, the idea is to assign a class, so a label, essentially. So the image classification is just this, giving to spectral classes, to spectral pixel, a class value, class name. And as you can see, this is, what you do essentially. From the spectral value, you give a label, essentially. So why? Because we can do a lot of things. I don't know, essentially what you are going to do, but probably will be in some of these three sphere I draw. So one can be policy or strategy for example, disaster risk reduction or environmental protection, or protection also of wildlife habitat, or for example, support agriculture for cropland areas, cropland production. But this is probably just a part of all potential application of why doing land cover mapping. So for example, supporting policy could be also understanding urban expansion, especially in Asian city where you have a rapidly increasing surface of artificial surface, giving to population growth. Another thing for me, it's important to provide a difference between the land cover and land use, which probably for you would be very silly to highlight in this code, but it's important for me. So essentially we can, with the land cover, we are just interested to the view of type. Land use essentially is how people are using the land. So for the same image, spectral image, we can have a different classification. Of course, in our case, we are interested in land cover, because to do a land use map, to understanding how the land cover is used, essentially, we need to have high resolution data, because you could see here, we need to understand if it's a specific building, is a specific function, is a residential, industrial, or things like this. So for us would be important land cover classification. And of course, it's a hierarchical classification. So based on the resolution and also the aim of the work, we can decide this is the CORIN, so it's the official land cover map used in Europe, whose map are based on Sentinel-2 data. You can see we have a level 1, which I would suggest to do tomorrow, essentially based on very broad classes, artificial surface, agricultural areas, forests and semi-natural areas, wetlands and water bodies. And then within that, you define different level 2, so higher details. So for example, in particular for probably studying of urban growth, could be very important to understand what these artificial surface are. So if it's a building, residential, commercial, is a mine, or is a road, for example. And actually, there are also another level I didn't add, which again, provide much more details of level 2. So these are the conventional land cover name. I would suggest probably tomorrow to use, yeah, just this level 1, which is already good enough. And of course, how it works, the length classification in general, is essential. We are looking at the spectral signature. So for this is important, having more bands, for example, here, 1, 2, 3, 4, 5, 7. It means we have more space to understand where the difference is. So you could see, for example, that let's say we have just a band. I hope you can see my cursor. A band centered at 1.3 micrometer. We don't see the difference between soil and vegetation. But if we have other bands, additional bands, we can use them, because you could see, for example, in the infrared, there is a huge difference between soil and vegetation. So it's important using as much bands as we can. But of course, we are using only the bands which provide the best resolution, the 10 meter, which for the Sentinel-1 are 2, 3, 4, and 8. So the blue, green, red, and near infrared. Okay. So for example, as you can see, for example, if we compare the spectral signature of 2 different bands, okay, band 3 and band 4, let's say it's this red versus near infrared reflectance value, we can see that essentially, for example, band 3 reflectance for water and vegetation is very similar. So if you see at the y-axis, but if we see at the band 4, the reflectance, okay, on the x-axis, it's much different. So it's important, as much bands information we can add, the better it is. So when we do a classification analysis, for this we tend to use as much bands as we can. But of course, even if we, for example, let's look at this vegetation. Okay, we should, of course, it depends from the type of level of classification we want. But again, why it could be easier distinguish between vegetation and soil? If we then to go add another level of detail, so the vegetation types, we need to consider that different vegetation types could have eventually the same spectral response. So that could be much more difficult. So in that case, would be much useful having even more bands than in this case 7. So for this, for example, as a mineral mapping, for example, we use hyperspectral data because we need, the difference could be so tiny between minerals in the reflectance spectrum that we need hundreds of bands to depict the differences. The same is also here, essentially. The more bands we have, the more details we have to understand the different type of vegetation, for example. So for this, I want to keep very broad and not go in details of the different type of vegetation, but just analyze, in this case, everything as forests and semi-natural areas or agricultural areas. Image classification approach. We are going to use a pixel-based. So essentially, every pixel is analyzed according to its spectral properties. That's it. And it's very useful to analyze the change in land cover. The object-based, instead, it takes in information not just from the spectrum, the pixel itself, but also from the object, so the shape. So we can define, also give some constraint on the shape of the object. And so in this case, we do what is called, before doing the classification, we define what is called a segment, an object, and then we classify that object. This is very useful for high resolution imagery, but it's very time consuming. We are not going to do this. We are going to do just a pixel based. And it's also useful, this object based, to reduce the speckle effect, so the noisy random pixel, which can be classified as a completely different class. I'll try, okay. An overview, we can do object-based image analysis, a segmentation in Google Earth Engine, but it will require a lot of intermediate steps. But this is just to give you an idea. So essentially, we consider spectral and spatial information of the object, like, for example, mean, standard deviation of the bands, but also size, shape, texture of these objects. So you could see for the same image, you could segment in different objects the same area. So we also consider not just the object itself, but also the relationship with the adjacent object. This is just to give you the full spectrum of what is possible. And then now that was the approach, pixel-based and object-based. Now, regardless of the approach, as I told you, we are going to do pixel-based classification. We then have to decide what type of method we are going to use for the classification. So probably you already know it. There are two main families. One is supervised. So essentially we define the training site, training area, and we say, okay, these are the characteristic spectrum for this type of land cover for example, artificial surface. So it will then automatically, according to the classifier we are going to use later, and later on I'll give you an overview also on that. The algorithm then, regardless of what type of algorithm, will automatically identify area similar to that training site. So you could see here, we give a vegetation field 1, vegetation field 2, 3, and then we do a classification. Unsupervised, instead, we use essentially automatically the pixel when are classified to a user-specified class. So we can, for example, say, okay, find 3 classes, and automatically it will find, based of course on spectral information, the classes. So, and then of course, once we have these groups, this cluster, we give a label to them, but we don't interact in providing training site. I think for us, it would be much better to start. So the example we are going to work tomorrow is a supervisor. So in the supervisor, you select training site, and you can eventually, what we can do is we can, eventually edit and classify again. If we are not happy, we can redo the classification in a loop. With the unsupervised, instead, no, we run a clustering. It's a clustering algorithm, and essentially we can run again and again, but what we can change is essentially very fewer parameters, for example, like the number of classes. I will give you now just a slide on the unsupervised, because it can be done in Google Earth Engine, but we're not going to use it, just to acknowledge it exists. So for example, the unsupervised classification classifier is a cluster analysis called k-means, where essentially we partitioning, let's say these are the 2 bands, so we are not now in the space domain, but in the spectral domains. So we partition our observation in a k number of clusters we define. And you could see here, the algorithm, essentially, the algorithm suddenly start, we say, okay, we want 3 classes. The algorithm will start defining these classes randomly. Then what is happening during each iteration, it will calculate essentially for each pixel, essentially the distance to, in this case, for example, the class means, and reclassify the pixel respect to the new mean. So we have these 3 classes, we calculate the mean, the spectral mean, and then we recalculate the distance and see if there is a much better way to have, let's say, a lower distance. This is called Euclidean distance. So this Euclidean distance, it means that essentially it's trying to find pixels which are very close in these spectral domains. So it's an iterative process, which can be quite long, of course, because if we don't set up any minimum condition. Another classifier is isodata. So again, we don't need, in this case, the number of clusters. The algorithm split automatically and merge this cluster. So we can define, in this case, threshold for the maximum number of clusters, the maximum number of recalculation. But again, it's always based on what is called Euclidean distance. So it classifies the pixel in a way, then it calculates so it creates some groups. It calculates then the mean for that group and calculate the distance from every pixel. And if there is a better cluster, it will apply that cluster. And then it will start again the calculation of the distance again. So you see, we have here these 5 arbitrary cluster. It defines these lines, so this group, these classes, and then it calculates the distance, okay, between the center of the classes within each of these. We should consider this circular pixel. And if there is a better way to have a smaller distance between this pixel, it will redefine new class. Okay, so there is very less involvement of the user involvement here. Supervised, so this is what we are going to use. So essentially in the supervised, we require the analyst, the user, to select training site. So, and we take those area, we select also validation area along with training site. So essentially in the training area, we say, okay, this pixel is a forest, a conifer. This other is water. This is a deciduous. So from this side, it takes the classifier, it takes the spectral signature, and in Google Earth Engine, we can select both or a pixel size or a whole polygon. Okay, having a polygon could be better because we take in account the variation within the same class. And we take the spectral signature. So this spectral signature are used for comparison and see if we found similar pixel. So for example, this is the image, the multispectral image. We define the classes and we want to classify this empty area. We don't know what it is. So the algorithms select this pixel, takes this, extract the spectrum, and then it compares and see what is more close to. In this case, I think it's conifer. So it's just a matching, okay? Of course, when we talk, so it's important for the exercise we are going to do tomorrow, how we select the training site. So usually there is a rule. Of course, this is just a not a fixed rule. It's just like a user experience based rule, where if we have n bands of data, we need 10 times n pixel of training data. The size must be large enough to provide estimate of property of each class. So for me, it's probably better not selecting single pixel for each class, but polygons. Location, it's better we have different training site for the whole image, because we can have still, even if we don't have any cloud coverage, we can still have some influence of the atmosphere in some part of the image, which can affect the extraction of the spectral signature. Number, we usually have not just one training site per class, no, it's several. And uniformity, so it's important we have a unimodal frequency distribution. So it's important we have like pixel, we have, or for example, is, let's say, water bodies. If we want to train water bodies, it's better we take, for example, water bodies for clear water, for blue water, let's call it. But also it's better we take also a training sample from black water, where water is darker, okay? And not we take both black and blue water together in the same class, because that would make this water class very variable. So it's better, yeah, we try to split and be uniform in that splitting. We can see tomorrow. So it's important that land cover types are spectrally similar. So for example, you could see an example here. We want to select a training site for agricultural areas. You could see here, it's better we took this type of training, because in this case, we have too much variability. We have a road in it, and also we have different vegetation with different reflectance. Okay, so it's much better to keep uniform training site. Of course, we should be aware of shadow and clouds. Also, it's important that training site are are not taking enough variability. So as I told you, the example of the water, it's better we divide black water from crystalline water as a training site. These are, okay, so these were the general rules for selecting training and validation site. This is something that we have to do regardless of the type of classifier. So the classifier is essentially, I will go back, how we match this with this, okay? The training site with the unknown pixel. So these are probably the 7 most used. I'm going to talk the last 4. I'm going to show everything, but the last 4 are the one available in Google Earth Engine. That's it. So these are the one we can play with tomorrow. So minimum distance and maximum likelihood. Again, it's like, as I told you before, for the unsupervised clustering classification. So essentially we calculate from those training sites a mean value for each class, and then each pixel is assigned to that class according to the Euclidean distance. These are, again, is not a map. This is not a spatial dimension. This is a spectral dimension. So we do this for how many bands we have? 7 bands. We do in 7-dimensional space, and we assign pixel to these classes. Maximum likelihood, in this case, we take the mean and standard deviation, okay, for each band. So we calculate essentially, because we have also the standard deviation, we also have a count of probability of pixel falling in that class, okay? But it's very similar to the minimum distance. The spectral angle mapping, in this case, sorry, can you give me 1 second? Okay, sorry. Spectral under mapping instead determines the similarity between an unknown spectrum and a reference spectrum. So essentially, we, instead of calculating the distance, we calculate an angle, okay, again, in a spectral dimension. So we treat essentially this spectrum as a vectors in a n-dimensional space, which is correspond to the number of bands. Cart. So cart is probably the example, yeah, we will start tomorrow, is a cart, yeah, definitely. Classification and regression tree. It's non-parametric machine learning, but also these other, they are all machine learning. It's just now we are going to label these things and makes more appealing and say it's machine learning, but also this. And this has been done for 30 years now. It's just now it's more, let's say, appealing. Machine learning to base it for classification and also regression. We will use, of course, for classification. We can use for categorical or numeric. In our case, it's numeric. What happened essentially is we split as a tree in different leaves our question. So essentially, in this case, the example is, for example, is the 8 above 180 centimeters? Yes or no? Yes, okay, it's a male. No, we do other question. The same in that case for our classification, there will be the band's value. Is band for value above 400 micrometers? Okay, so that's that's, for example, forest. Or eventually we can add other question on it. So we have, like, in this tree, a recursive partitioning. So we can, of course, partition the data, the population in different class, spawning this question. So we have, like, our questions, then the split point, okay, very sharp, okay, and then we have a node. So this node represents essentially the label we are going to provide, okay. Growing tree. So this is an example. We have our pixel. These are our bands value. Okay. So what we will do is essentially we will ask what is red minus what is below 0.43 will be red, while what is above 83 sorry. Sorry. So if it's so this is our question. If it's above 6.8, yes or no. So if it's above, okay, we have, you can see here, a blue value. If it's below, it's red. Then, of course, we can add other question. We can add also these other band information, split again. If it's B above 5.4, okay, let's define red here. If it's below, will be green. Again, we can say also other node, okay? So you can easily split again and again. So you could see this tree can grow and grow. And then we will have like our calculation of the error. So how many, for example, red pixels have been classified wrong, and the same for green and blue. But in the end, again, it's a splitting. So we start with this band, for example, band A. We ask, okay, what is below and above 6.8? Then we ask, okay, let's consider also band B, and so on. So this is how it works. So it's a growing tree. Random forest, again, is machine learning. But while for decision tree, we have just one tree, here we have more trees, so a forest. So that is the way they call in this way, why they call it in this way. So it's a randomly created decision tree. Each node works on a random subset of features to calculate the output. The random forest combines the output and then, yeah, generate the final output. So it's like the decision tree, but there are much more tree, essentially. Because what happened is essentially the main limitation of this card could be that one tree could not be enough. So we need more way to define these classes, classify these classes. So you could see here, we have a data set and it is randomly, so it's a random, split in different trees, okay? And then we have, based on the, we calculate essentially for that data set, what's the label, and then based on the majority, we give the label, essentially. We assign the class. So it could be that this class is agricultural land, this is agricultural land, this is artificial surface at the end of this tree. So in the end would be agricultural land, okay? So these are all the information because you want to go in deep in this algorithm, but this is just to give you the overview and also to stay on time. Then we have naive Bayes. So Carter random forests are discriminative. Naive Bayes instead is a probability model. So it is based on the Bayes theorem. So essentially what happened is apply the Bayes theorem with a strong independence assumption between the features. So what happened is we know the a priori, so our training side, we calculate the likelihood and then we calculate the a posteriori probability, then we redefine the priori and we recalculate again the likelihood. So this is based on the Bayesian theorem. Yeah, so it's an iterative process. And it's very, to be honest, this naive-based classifier is very efficient. It's less computationally intensive of, for example, random forest and card classifier, and requires a small amount of training data. Yeah. Then we have the vector massing. So essentially we find in this case, we have a training example, our training site. Each belongs to, in this case, let's say these two categories, okay, black and white. And essentially what we do is we create essentially what is called hyperplane, this case, in n-dimensional space where this is related to, in this case, the number of bands, which distinctly classify the data points. So these are our hyperplane. We could try, for example, having this hyperplane one first, this second hyperplane, and every time we calculate this distance. You see, we calculate what's distance from these are what are called the support vector, this distance, this distance parallel to this hyperplane. But of course, if we draw the hyperplane here, we still have some black point out of the hyperplane. The same for hyperplane 2. Hyperplane 3 instead will provide a good way to differentiate between this black and white pixel. Okay. And of course, now regardless of the classifier, in the end, we have an accuracy. So we, as I told you, we have for the supervised, the training side, but also the validation side. So it's side we define at the beginning, and we say, okay, this side, whatever the classification would be, has to be water, for example. These other should be forest. And we use them to assess how good is our classification. So for example, let's see. This is the class assigned by the classifier at the validation side. So the classified map. And this is the class we define at the beginning, along with the training side. So essentially we say how much of this, over this side, how much of this water really correspond to water class in the classified map. And of course you could see 21, the majority, but of course we have also 6, which belongs essentially, which are forests, but they are essentially in training side that we knew they have to be water. Okay, and the same for example, this is the validation side we define as a forest. We see that 31 of this side correspond to forests in the map, but actually there are 5 and 1 which not correspond to other classes. So in the end, if we see the diagonal value, we can extract the diagonal value are essentially this comparison between reference and classified data provide us, you see, the accuracy of the map, the overall accuracy, which is around 78%. But we have also other type of error here. So for example, we have which could be important is, for example, the producer and we have for each class an accuracy. So for example, we have the producer accuracy, which is 21 to 33. So essentially in this case, this is what is called the error of omission. So of these 12 sites, essentially, they are omitted from water and classified as a forest or as a urban, okay? The same here. So this producer accuracy is 64%. So what does it mean? That while, for example, for forest and urban, this omission error, exclusion error is quite good, we need to change some of the training sites. So the training site for water, they are quite bad, okay? And this user accuracy instead is essentially based on the inclusion. So how much of, for example, forest site were erroneously included in the water, okay? So again, these are important, this error on a class basis to know if we have, for example, to change the training sign or if the classifier is wrong. So it's not just the overall accuracy. And for tomorrow, yeah, we are going to start doing a Lankover map with a pixel-based approach, with a supervised method and the classifies card. But of course, we can eventually be flexible and decide to change the classifier. It's literally once we define the training and validation side, we can just change a column, a line in the text, in the code, and we can do all the classifier we want. So that was it, the presentation. I will stop recording.